Hello everyone, myself Soumya BG, Assistant Professor, Department of ECE, SJBIT. The subject is Digital Communication and the subject code is 18AC61. We are discussing about the Module 4 topics. The topic is Channel Equalisers. Till now, we discussed about the design of transmitting and receiving filters for digital PAM transmission when the frequency response characteristics of the channel are known. The design of these filters for zero ISI at the sampling instance are being discussed. And this design methodology is appropriate when the channel is precisely known and its characteristics do not change with time. But practically speaking, the frequency characteristics of the channel are unknown and they will vary with time. And the equations of such time varying channels are radio channels. These channels are characterized by time varying frequency response characteristics. Under these circumstances, we will design the transmitting filter to have a square root raised cosine frequency response. We are intended to design the transmitting filter which is having a square root raised cosine frequency response. This is given by GT of f equal to square root of x RC of f exponential of minus j2 pi f t naught mod f less than or equal to the bandwidth w and 0 whenever the bandwidth, that is the frequency, lies in the range which is greater than w. And in such cases, the receiving filter will be having a frequency response GR of f which is matched to the GT of f. This is GT of f. This is not GRFF, this is GT of f. Hence, in such cases, we can tell that mod of GT of f into mod of GR of f is equal to the cosine function XRC of f. Mod of GT of f into mod of GR of f is equal to capital XRC of f, which is the raised cosine frequency response. Now, due to the channel distortion, the output of the receiving filter can be expressed as y of t is equal to summation n is equal to minus infinity to plus infinity a n x of t minus n t plus w of t, x of small t minus n capital T plus w of t. Here the x of t, as we know, it is equal to gt of t convolved with c of t convolved with gr of t. I repeat, the x of t is a convolution of gt of t with c of t, which is again convolved with gr of t. Now, the filter output may be sampled periodically to produce the sequence which can be expressed as ym equal to summation n is equal to minus infinity to plus infinity a n x of m minus n plus w m. This we can expand as x naught a m plus summation n is equal to minus infinity to plus infinity, but n value will not be equal to m, and the value is a n x of m minus n plus w of w m. Here x n is nothing but the sampled value, that is x of n with capital T. N value ranges from 0 plus or minus 1 plus or minus 2, it continues. In this expression of ym, we already know that the middle term in this RHS of the equation represents what? The inter-symbol interference, ISI, inter-symbol interference. Now, in this equation, what is our information sequence? The information sequence is AM. Now, in order to detect the information sequence AM, we are using a maximum likelihood sequence detector. maximum likelihood sequence detector, because this is one of the optimum detector. But with this detector, the computational complexity will be very high, as well as practically speaking it is very difficult to design, it is very impractical to design. Hence, we go for sub-optional methods, in which again ML detector, it serves as a benchmark for the comparison of its performance. In order to detect the information sequence AM, we can go for a maximum likelihood sequence detector ML, but this detector's computational complexity is very high, as well as it is practically speaking difficult to design. So, we go for some other methods, in which again we use this ML detector as a benchmark for the comparison of the performance. Now, let us discuss one of the type of equalizer called linear equalizers. Where we are supposed to use these linear equalizers? We need to use these equalizers at the output of the receiving filter, and these linear equalizers are particularly used for the channels whose frequency response characteristics will be unknown, as well as they are time variant. I repeat, the linear equalizers will be used for the channels whose frequency response characteristics are unknown, as well as they are time variant. In such cases, we go for these linear equalizers, and they will be used at the output of the receiving filter. Now, coming to the block diagram of the equalizer, this is the block diagram of the equalizer, in which we have got the input as the input data, that is given to transmitting filter with the response GT of f. The output of the transmitting filter is given to the channel with the response C of f. Now, the output of coming from the channel will be added with the noise N of t, and the output of this channel will be given to the receiving filter having the response GR of f. And finally, after the receiving filter has high repeat, the equalizer will be used, which is represented by the response GE of f. The output of the equalizer will be given to the detector. Now, the design characteristics for a linear equalizer, they are taken from a frequency domain initially. That is why I told the response of each filter, whether it may be in the transmitting filter or the receiving filter or the channel or the equalizer, in the frequency representation. Here the demodulator consists of the receiving filter with the frequency response GR of f, which is followed by the channel equalizing filter, which is having a frequency response GE of f. Now, we know that this receiving filter GR of f and the transmitting filter GT of f are matched. They are matched filter. So, they satisfies the equation mod of GT of f into mod of GR of f is equal to the cosine, raised cosine function, that is capital X RC of f, the raised cosine function capital X RC of f. The channel equalizing function, that is G of f, this is mainly used for what? It is mainly used to compensate for the channel distortion. Hence, we can tell that this equalizer frequency response must equal the inverse of the channel response. Since it has to compensate for the channel distortion, this equalizer frequency response, it has to be equal to the inverse of the channel response in order to cancel that distortion. Hence, we can write G of f as equal to 1 by C of f. This C of f can be written as mod of C of f into exponential of j theta C of f, and this exponential of j theta C of can be written in the numerator as exponential of minus j theta C of f. Here the mod f value should be less than or equal to w. It has to lie within the bandwidth w. And now, when we take the magnitude of this G of f, that is mod of G of f will be equal to 1 by mod of C of f, and theta E of f will be equal to the negative of theta C of f. Theta E of f, the phase of the equalizer, will be equal to the minus phase of the channel theta C of f. Now, in this case, The equalizer is said to be the inverse channel filter to the channel response. I can tell that the equalizer is the inverse channel filter to the channel response, and this inverse channel filter, it will completely eliminate the ISI to 0, and at this is being done at the sampling times t is equal to nt. Therefore, the equalizer can be called as a zero forcing equalizer. The equalizer can be called as a zero forcing equalizer. Whatever discussion we did with respect to the equalizer, that it is the inverse of the channel response. Due to this channel filter completely eliminates the ISI to 0 at the sampling instance t is equal to nt, and hence the equalizer can be called as a zero forcing equalizer. In such a case, the input to the detector will be of the form Ym is equal to Am plus Wm. In this equation, Ym is the noise component, which is a zero mean Gaussian with the variance defined as tau omega square is equal to n naught by 2 integral of minus w to w mod of xrc of f divided by mod of c of f the whole square into df. In general, I can tell that the noise variance at the output of the zero forcing equalizer is higher than the noise variance at the output of the optimum receiving filter mod of gr of f. According to this equation, now we can come to the conclusion that the noise variance at the output of the zero forcing equalizer will always be higher than the noise variance at the output of the optimum receiving filter, that is mod of gr of f. Now let us discuss how to design these linear equalizers in time domain. The design of linear equalizers in time domain. In real channels, the ISI is limited to a finite number of samples. Let us say that those samples are L samples. The ISI is limited to finite number of samples in real channels, not in ideal channels. In ideal channels, we will not be able to predict the number of samples. Practically speaking, in real channels, it is limited to only L samples. Therefore, a channel equalizer is approximated by a finite duration impulse response filter, this FIR filter, or it can be approximated by a transversal filter with adjustable tap coefficients, Cs, as we can see in this diagram. This is our unequalized input, and this actually represents the algorithm for this tap gain adjustment, the Cn gain adjustment, and this is the summation that is resulting in the equalized output. The unequalized input results finally in the equalized output. In this diagram, which we are depicting finally for the design of the linear equalizers, the time delay tau between the adjacent taps may be selected as large as capital T, which is the symbol interval, in which case the FIR equalizer can be called as a symbol spaced equalizer. The FIR equalizer is called as a symbol spaced equalizer whenever the time delay tau between the adjacent taps it is selected as large as T. But in this case, the frequencies in the received signal above 1 by T value will be aliased, and hence the equalizer compensates for the aliased channel distorted signal. But in this symbol spaced equalizer, whenever the frequencies in the received signal above 1 by T are aliased, the equalizer will compensate for the aliased channel distorted signal. Now, when the time delay tau between the adjacent taps is selected in the range 2W less than or equal to 1 by tau greater than or equal to 1 by T, when the interval is within 2W less than or equal to 1 by tau greater than or equal to 1 by t, aliasing will not occur. And the inverse channel equalizer, it compensates only for the true channel distortion. In such cases, the aliasing will not occur, and I can tell that the inverse channel equalizer, it compensates only for the true channel distortion. Now coming to the third case in which the time delay tau is less than t. The channel equalizer is said to have a fractionally spaced taps. The channel equalizer will be having a fractionally spaced taps which is very less, and in such a case we call the equalizer as fractionally spaced equalizer. So we came across three cases here. In the first case, the time delay tau is large as t, and the equalizer is called as a symbol spaced equalizer, and the frequencies in the received signal above 1 by t in this case will be aliased, and the aliaser will actually compensate for this distortion. Now coming to the second case in which the tau is selected such that 2w less than or equal to 1 by tau greater than or equal to 1 by t. In this range the aliasing will not occur, and the equalizer compensates only for the true channel distortion. Coming to the third case in which tau is less than t, it is the symbol interval. The channel equalizer will be having a fractionally spaced taps, and in such a case we call this as fractionally spaced equalizer. This is about the linear equalizer, what is linear equalizer, and how to design the linear equalizers. Now coming to the equations governing this linear equalizer, the impulse response of this FIR equalizer can be represented as GE of t is equal to summation n is equal to minus n to n Cn delta of t minus n tau. The impulse response of the FIR equalizer is given by GE of t is equal to summation small n is equal to minus capital N to capital N Cn delta of t minus n tau. This we can take as equation number 1. And correspondingly the frequency response can be written as GE of f is equal to summation n is equal to minus n to n Cn exponential of minus j2 pi fn tau. The frequency response is given by GE of f is equal to summation n is equal to minus n to n Cn exponential of minus j2 pi fn tau. This we can take it as equation number 2. In these equations, the sequence Cn are nothing but 2n plus 1 equalizer coefficients. The Cn sequence represents 2n plus 1 equalizer coefficients, and n is chosen sufficiently large. The value of n can be taken as 2n plus 1 greater than or equal to capital L. Now since x of f is equal to gt of f multiplied with c of f multiplied with gr of f, because x of t is equal to gt of t convolved with c of t convolved with gr of t, and in frequency domain x of f is nothing but the multiplication of the frequency representations of transmitting filter, the channel as well as the receiving filter. And small x of t, as we know, it is the signal pulse corresponding to capital X of f. Taking into consideration the equalized output signal pulse, it can be represented as q of t is equal to summation n is equal to minus n to n Cn into x of t minus n tau. Taking into consideration these expressions of impulse response, the equalized output signal pulse can be written as q of t is equal to summation n is equal to minus n to n Cn x of t minus n tau. This we can take it as expression number 3. Now at t is equal to mt, we can write this equalized value as q of mt is equal to, this is t is equal to m capital T. T is equal to m capital T. In such a case, Q of mt is equal to summation n is equal to minus n to n Cn x of mt minus n tau. The sampled value Q of mt is equal to summation Cn x of mt minus n tau. M value ranges from 0 plus or minus 1 up to plus or minus n. We can take this as equation number 4. Since in this equation we have 2n plus 1 coefficients, we can write this equation 4 as Q of mt is equal to summation n is equal to minus n to n Cn x of mt minus n tau, that is equal to 1 whenever m is equal to 0, and for the remaining values, that is m is equal to plus or minus 1 plus or minus 2 up to plus or minus n, this Q of mt will be equal to 0. I repeat, since 2n plus 1 coefficients are there in equation 4, I can rewrite this equation 4 as Q of mt is equal to summation n is equal to minus n to n Cn x of mt minus n tau, that is equal to 1 for the value m is equal to 0. For the remaining values of m, that is m is equal to plus or minus 1 plus or minus 2 up to plus or minus n, the value of Q of mt is equal to 0. This is expression number 5. Now this can be expressed in matrix form as capital X C is equal to Q. In matrix form, this is capital X C is equal to Q, where capital X is a 2n plus 1 into 2n plus 1 matrix with elements x of mt minus nt. Capital X is a 2n plus 1 into 2n plus 1 matrix with elements x of mt minus nt, and C is the 2n plus 1 coefficient vector. The small c is 2n plus 1 coefficient vector, and Q is the 2n plus 1 column vector. Q is the 2n plus 1 column vector with one non-zero element. I repeat, in the matrix form, it can be written as capital Xc is equal to Q, where X is a 2n plus 1 into 2n plus 1 matrix with elements x of mt minus nt. C is the 2n plus 1 coefficient vector, and Q is the 2n plus 1 column vector with one non-zero element. This FIR zero forcing equalizer, it will not completely eliminate the ISI because we are considering it to be having a finite length, that is L. But as n is increased, the residual ISI can be reduced, and as n tends to infinity, the ISI is completely eliminated. As the value is finite, the ISI cannot be eliminated properly. But as n tends to infinity, the ISI is completely eliminated. So finally, we understood what is the necessity of equalizers, how to design a linear equalizer. We come across the equations pertaining to the linear equalizers, and finally we came to the conclusion that for a finite length, the ISI cannot be eliminated completely, but as n tends to infinity, it can be eliminated. Thank you.